Processing of 3D data from surface sensors such as radar, sonar, etc. And we have already talked about, first of all, low-level, how the data is acquired in the first place, how to smooth that data to remove noise in some general sense, and then how to align multiple viewpoints of the same object together. So now we're going to talk about how to combine those individual views of a single model or a single area together into a unified, single, complete model. Now, just as a reminder, our goal for this lecture anyway, is going to be to create 3D models of objects from multiple 3D scans. So if you have an object like that gnome, you can imagine having one of your laser rangefinders that uses time of flight or triangulation and taking multiple shots of it from multiple viewpoints and getting 3D scans that look like so. And if you paid attention, not last time, but the time before last on Monday, you learned about how to solve for the rotation and translation that aligns these things together. And if you do that, and you kind of plop all of them on top of each other after you do this alignment, you can get something that looks like that. So it looks like we have completed the task of building a complete 3D model of the gnome after we have aligned all of these surfaces together. And by the way, the motivation for why we do this should be clear. So if you want to animate this little guy for a video game or a movie, you would want to have a complete geometric representation of the entirety of the object. And similarly, everywhere where I said the little gnome guy, you can imagine replacing that with 3D scans of a particularly interesting hill and valley area on Mars, where you want to build a complete, large-scale, unified 3D model that you can fly through. So again, let's say that we have done this job of aligning all of our pairs of 3D views, or all of our several 3D views of the object together, so that in toto, if you look at all of them together, they cover the entire object. So the question is, are we done? Can we say that we have completed the job of 3D modeling? Not exactly. That's why there is a lecture today. So first of all, multiple aligned meshes don't form a well-defined surface. And just as one concrete example of that, imagine that I have this point on the surface that is imaged from 5 different data sets. Or in other words, from 5 different points of view. And let's for the moment forget about the discrete sampling of surfaces issue that we have talked about a couple of times. And imagine that we just happen to get points in each one of those 5 data sets that correspond exactly to this location on the surface. That means that when I store my representation of the object on disk, I have not just one indication of the position of that part of the surface, but 5 identical ones that are overlapping with each other. So it's redundant. So the thing that we want instead is a single set of points and mesh faces, or in other words, edges that connect the points together, such that this part of the surface is only represented exactly one time. So there's a couple of reasons why we would need this. First of all, if we want to compute surface features, a lot of times what we're going to do is take individual points on the surface and calculate features with respect to that point. So this is sort of like an egocentric view of features where you consider yourself living at a particular location on the surface, such as this point right here, and then look around you at all the other points in your vicinity and say something about how those points on the surface are distributed. So if in my data set, if I have 5 identical versions of the same point in my data set, that means I'm going to basically calculate 5 identical sets of features, each one corresponding to the same exact location on the surface. And furthermore, each one of those feature vectors is going to represent basically multiple identical points in it, which is confusing. So this gives an example of what we're going to try to do today in today's lecture, going from this set of views of the object that are all overlapping with each other to this thing, which is basically a merging of all of these disparate point sets into one unified one. And then once you do that, you can texture map it either using information from your sensors if they were friendly enough to give you not just 3D point positions but a sense of color as well, or you can color that thing in yourself. So I just described this. Here's a handy visualization of why having multiple overlapping surfaces, parts of the surface, having multiple representations of the same part of the surface over and over again, why that is potentially bothersome. Here I'm showing two views of this figurine on the left. One of the 3D scans of the surface is shown in brown, and the other one's shown in gray. And now imagine if we slice through these two aligned views using a plane here. So if I do that, then you'll see that this part of the surface is represented by both the brown part and the gray part. And again, what I'm going to do to compute features of the surface at this point is to summarize in some way all points on the surface that are in this neighborhood, which is going to include the brown points and the gray points both. However, over here, where I only have this part of the surface represented once, that's not going to be true. I'm going to have representations of this part of the surface that only basically include the gray points. So features from here are going to differ from features from here for no especially good reason other than that I happen to image this part of the surface multiple times. So it's redundant and it's confusing. And it can give you surface features that differ from each other for no especially good reason at all related to the geometry of the object. Another issue is that if you are one of these computer graphics people that is making a movie, or if you are a video game person, that, imagine that you have giant monster squirrel attacks the earth video game where you want to render this thing, what you are going to do is essentially simulate a fake light source giving off light, bouncing off of the squirrel here, and bouncing into the CCD array of a fake camera. Where the reason why it's computer graphics is that you get to decide all the characteristics of the light source, how bright it is, where it is, and so on, and you get to decide where the camera is. That's what makes it computer graphics. It's made up by you. Now, in order to do that, you're going to do a set of operations, and this is actually, this problem has been studied into the ground in computer graphics, but you're basically going to take a set of photons that come off the light in certain directions and determine where exactly that photon bounces off your surface. So what you're going to do basically is consider all possible mesh faces or all possible mesh points and determine if the photon appears to hit that part of the surface on its direction of travel. So that means that if you have multiple parts of your surface that represent the same thing in the world, you're basically going to calculate that the photon bounces off of this part of the surface. But you are still going to check for whether or not it bounces off of this part of the surface as well, which doesn't make any sense because they occlude each other. And really the only thing that you want is to make one check for whether or not the photon bounces off of this part of the surface and this part of the surface and this part of the surface, and you're going to end up doing that test twice. And furthermore, something funny is going to happen at this boundary, where suddenly there's going to be a rift where photons bounce off of a part of the surface that's closer to the camera, and then there's going to be a step where the photons bounce off of a further away part of the surface. And in a worst case, where the light is located over here, this part actually might cast a shadow on this part, which is not good at all because they're exactly the same surface. So hopefully that makes sense. And the simplest thing to consider is the conciseness argument, or how much room on disk is your 3D model going to take up? How much room is it going to take up in main memory, which basically drives how large of a model you can manipulate in a reasonable amount of time. So let's say that each one of our points of view of our object from which we collect a scan gives us a scan that has n surface points on it. And there's k of them, and we've aligned all those together. So to store the entire set of aligned meshes together as our representation of the object, we need something like n times k bytes, or some multiple of n times k bytes. Some fixed number of bytes, say 6 or 9, for every 3D surface point. So usually what happens is that the intrinsic complexity of any object is a fixed thing. So if you have just a very simple sphere or a plane, the number of bytes that you should need to represent that thing should be relatively low and completely independent of the number of times you scan it. You can scan the top of this table 10 times, and it should take you a certain number of bytes to represent the whole thing on disk. If you scan the same object 50 times or 100 times, that shouldn't make your representation of the table more complicated, because the table is not complicated. It's a simple thing. But now, if you think that through, what's actually going to happen is that if you get more scans of your object of interest, you're actually going to take up more space to represent it, regardless of how complicated the object itself is. So it should be counterintuitive to just keep representing all of the aligned surfaces as you keep piling them up. So now, our problem, which this is leading up to, is that we are going to align all of these meshes, or all of these surface representations, together in the same space. And now what we want to do is reduce all of them to a single set of points and faces that form a single, unified, well-defined, closed surface in the intuitive sense that there is one surface point for every position on the real-world object. So here is your recipe slide, which is, if you haven't noticed, is what I like to do. Basically, there are two main schools of approaches for solving this problem. One is mesh-based, and you can think about this for those of you who sew, which I don't think is too many because people don't really do a whole lot of sewing anymore. I can't sew hardly at all, but this is the analogy of thinking of two of your surfaces as being two pieces of fabric, putting them together to form a seam and sewing them together. So usually what happens when you sew two pieces of fabric together is that you overlap them to some degree, you sew them together, and then you have these two little flaps of fabric on either end of the seam. Well, a lot of time those are on the inside of your, those are on the inside of your clothes, but you can imagine actually cutting those off so that there really is no pieces of fabric that are flapping off, and that it ends up looking like this, where it's just one piece of fabric, seam, and then the other piece of fabric. This is basically what mesh-based approaches to combining meshes together does. So you keep sort of splicing or sewing. The actual, one of the main algorithms in this area is called zippering. And that might even be a more apt idea, which is that you first take your pair of meshes, you put them together in their aligned way, you cut off the parts that are redundant or that are extraneous, and then make a zipper that zips the two together. Volumetric approaches are different, and they don't have the same kind of intuitive analogy. But for here, what you're doing is instead of representing each of your meshes and how they relate to each other, you go back to this idea that all objects live in an ambient space. Remember I talked about if you deform an object, you can think about the object as being embedded in jello, which is sort of like your ambient space. And as you deform the object, you deform the jello. Well, this is kind of like a jello-like approach to putting multiple meshes together into a unified version of the same model. What you do is you think about every location in the 3D world, and you ask yourself the question, does at least one of the meshes go through this part of the world or not? If not, it's not on your surface, and if so, it is. So I said at least one, which means that if you have 2 or 3 or 4 or 5 meshes that go through the same point in the world, then you just simply say that the mesh goes through, that the surface goes through there. And so in this way, you kind of just reduce every position on the Earth to a yay or nay decision about whether the surface goes through there or not. So we'll talk about both of these in more detail. One thing that I'm not going to talk about is the slightly different problem of what to do when you have just a set of points with no connectivity information. So it turns out that most practical real-world 3D sensors give you connectivity information from the scanner. So the thing that you get off of the scanner is not a 3D point set, but actually a mesh. But there are some sensors that just give you a so-called point cloud with no sense of how they are adjacent to each other. So for those, there's a rich literature on how to go from a completely unorganized set of points to a surface, but we're not going to talk about those in this class because I don't have time. And actually, it's these kinds of approaches that where you really get your bang for your buck is in higher dimensions where the points don't represent something geometric. You just have a point cloud of some kind of data in a high-dimensional space, and you want to somehow get a sense of what kind of high-dimensional surface they live on. But we don't have time to talk about these. I would suggest looking into, if you're a graduate student, there is a computational geometry class that's offered, I think, once a year, once every 2 years, that spends a significant amount of time on this. And it's in the winter. So that's Dr. Amenta teaches that, yeah. And let's use the mic. Okay, so that's your recipe for how you might solve this problem if you were an engineer. So of the two, let's talk about mesh-based approaches first. Consider that I have two meshes that overlap with each other, the red one and the yellow one. Well, you're simply going to do the kind of sewing idea, which is to first look at where the two meshes intersect with each other, which is right there. And then you partition the mesh into sections based on those intersections. So here I've taken the red guy and partitioned it into red and green. And the yellow one is now partitioned into yellow and cyan there. So then, if you are able to reason about which of the partitions are intrinsic to the surface and which ones are redundant or unimportant for or basically redundant or overlapping, then you can essentially, you've reduced your problem of determining, of combining meshes to identifying what sections of the meshes are overlapping and then just removing them. So if you do that and you're successful, you can figure out that the green part and the cyan part are redundant, remove them, and then combine the meshes together at these intersection points. So that's if you're successful at doing that. So this is, again, the analogy of two pieces of fabric coming together. You sew them together, and then you cut off the extraneous fabric. So this is all quite simple in principle. It's actually kind of a bear to implement in practice. So let's see. How to determine whether a mesh face or one of those segments is redundant or not. So one thing you can do is say, well, if a particular face on one of my segments or one of my partitions has a closest point distance to one of the other segments that's very, very low. In other words, if this one is proximal to one of my other segments of mesh data, then I will assume that that is redundant. And furthermore, if it looks like that part of the surface has surface normals that are nearly identical to the other part of the surface that it's closest to, then it also appears to be redundant. And also, it can't be part of the boundary. So, which is to say where the object stops. So this is basically saying that if two parts of the surface, two distinct data sets in your representation of the surface look a lot alike, one of them is redundant. So this is fairly simple ideas. So then, if you are able to do this and remove the redundant parts of the surface, you are left with dealing with this seam, which is to say, if you take two surfaces and intersect them, you will have a line or a contour of intersection where they intersect each other. And if you do that, then you will end up with a complicated looking boundary where, if you can imagine it, the surface on the left is coming out of the board like this, and so is the surface on the right, and they intersect with each other like so, and the gray guys are the parts that are sticking out and are redundant. So if you remove those, then you have to do some kind of, you have to use some method to triangulate the surface so that you end up with a unified representation of the surface where everything is a triangular face. And if you do, you'll end up with something that looks like so. So you actually have to be kind of careful about how you sew the two surfaces together after you discard the redundant stuff. Because you could end up with a set of teeny tiny little triangles which may or may not accurately represent the shape of the surface that underlies it. Another thing you can do is to consider the effects of noise on your acquisition of the data sets in the first place. So think about a sort of a worst case scenario would be that you have taken two scans of the same perfectly flat part of the object that's shown in blue, and your two scans are noisy because, as we have discussed, any sensation of anything at all has noise in it. But in this case, the noise is particularly a little bit severe, so that the yellow mesh, when you sense this part of the surface, you get a data set that looks like this, and for red, you get a data set that looks like so. And so using what I've just told you, what we would do is identify that there is an intersection between the two meshes here, here, and here. And then if we do a good job of removing the redundant parts of the surface, we'll basically remove this part, and this part, and this part. So then what we'll end up with is a rocky, bumpy representation of the surface where the part, where the scan that happened to introduce noise that made it closest to the sensor in the first place wins. So instead of getting a flat thing, you get a bumpy thing. Well, what you can do in this case is use the techniques I talked about in the last slide to basically identify that these two parts of the surface are very, very similar because they have similar, their closest point distances to each other are very, very small, and their surface normals are not the same, but they're very similar. And you can, instead of just removing the yellow one and removing that, you can average them together. And so that the thing you end up with is not just a simple conjunction of two pieces of surface, but it's something of an average between them. And if you do that, then the hope is that you will end up with something that is more flat, more like the actual underlying surface, and it kind of uses multiple sensation of the same part of the surface to average out the noise instead of kind of representing it. And the example on the right here shows what can happen if you do this. On the telephone receiver, if you take two 3D scans of it, it turns out that you're scanning of these parts that are closest to the receiver ends end up being fairly noisy. And so you can see that there are these kind of pockmarks that it's hard to tell whether it's that bas-relief ambiguity where you can't tell whether this is actually a ditch going into the surface or whether it's a plateau coming out of it. But it's actually a plateau for this reason. And what happens if you do this averaging out instead of just picking out parts of the surface to keep is that these more or less average each other out. So the hills and the valleys average each other out. Does this make sense? Okay. So here's another example of how you can take two aligned meshes, and things that I show in red are always a pain to project well. I think it has to do with the projector. But here's another example. Now here is actually kind of a difficult area for these mesh-based methods. So as you can see, what happened is that there's basically a lot of noise at the 90-degree angle where the receiver goes from this orientation to that one. And so if you were to simply represent the two meshes together in the same in the same data set, you would see there are all these jagged bumps coming out of the edge which don't represent anything in the real world. And if you zoom in and kind of take a receiver's eye point of view, you can see that there are all these triangles from the one mesh that are popping out. Some of that is actually due to misalignment a lot of times, but some of it is due to noise in the acquisition. But if you're smart about removing overlapping pieces of surface and combining multiple parts of the same surface to average out noise, then you'll end up with a unified representation of it that looks like this, where all of that redundant and noisy stuff has been removed. Oh, and by the way, it would be nice if this was shown in gray, but these are the two views. So you have, so this thing is shown over here in gray, and this thing is shown over there in red. Okay? So here's a failure mode for these things, something for you to consider. All right. What I've told you is that the only way to remove redundant pieces of surfaces is to look at intersections between them. And then you partition each of the surfaces into segments corresponding to where they intersect, or corresponding to the intersections, and then contemplate whether two pairs of surface segments should be averaged together or removed based on how similar they are to each other. So in other words, if there's no intersections, there's no action. If the two meshes don't intersect with each other at all, you don't remove anything. So now here is an obvious failure mode where these two surfaces have been aligned to each other, but they just simply don't intersect with each other at all. The red here and the yellow here clearly correspond to the same object in the real world. Same goes for this and this, but you're not going to remove anything because they don't intersect with each other. So that's an obvious failure mode. And one hack to avoid this is to basically fatten up each of your segments of the surface, or to fatten up each one of your faces, so that instead of having an infinitely thin edge that connects these 2 points to each other, you have a widened kind of blob-like cylinder that connects the two to each other. And then you can do cylinder to cylinder intersection to figure out that this segment intersects with, it really should be considered as redundant with that one. And this, the figure on the bottom tries to show you that idea, and whether it does so or not is an open question. So this guy here would represent one of the faces, or one of the faces of your surface mesh, and you're basically going to induce these walls that come out from it, kind of normal from it, to thicken it up. And then you're going to, the intersection problem has become more complicated, because you need to basically, instead of doing a plane-to-plane intersection test to figure out if the two separate meshes overlap with each other, you have to do this fat slab versus fat slab intersection test to see if the slabs intersect with each other, which is more time-consuming. Okay, so any questions about mesh-based methods before I talk about administrative stuff and then go on to volumetric approaches? Okay, administrative stuff, there's a midterm on Monday. Hopefully you all know about that. The homework 1 deadline, if you want to get 20% fewer points than you would have for turning it on time, the deadline for that is tonight. Homework 2 is available, and you should start on it, please. Any administrative questions? Okay. If that's the case, then we will move on to talk about volumetric methods, which, again, do not have the intuitive sewing analogy associated with them. What we are going to do is, again, go back to our same hypothetical pair of 3D surfaces, 3D surface views that we are going to try to unify into a single 3D model, and create a grid of cells that spans the entire k-dimensional space, or all of the jello that your object is living in. Okay? And that's represented here for 2-dimensional type objects. So then what we're going to do is we're basically going to throw each one of our component meshes, or each one of our surfaces from a particular point of view, into this world and compute what I talked about earlier, which is the occupancy of each cell in that grid. So simply put, you are trying to figure out whether each cell in your grid is occupied or not. And that sounds like a yes or no question, but you can actually make your algorithms more robust by trying to determine the probability that a cell is occupied or not, or the degree to which a cell is occupied or not. So as you can see, what I've done here is I've taken each cell in my grid and just simply decided whether the surface intersects with it or not. So this cell, this cell, this cell, and this cell are all occupied according to my decision that the surface goes through there. So then what we can do then is essentially convert our set of surface meshes into one occupancy grid. This is called an occupancy grid. And then remove the original meshes that we started with. So once I calculate these occupancies for all of our individual points of view, I can basically throw away the original meshes that gave rise to the occupancy in the first place. And that should be your clue that using volumetric methods allows you to reduce the amount of data. So if you take 50 scans of an object, if you take 100 scans of an object, if you take 200 scans of an object, you will still end up with just an occupancy grid. So really the amount of space required is determined by the space requirements of the occupancy grid. And all you're going to do by taking more scans is getting a more refined estimate of whether or not any individual grid cell is occupied or not. So then you throw your original meshes in here, you compute occupancy, and then the next part is to compute a surface that approximately wraps itself around the set of occupied cells in some sense. So just take my word on it for the time being that there exists such algorithms that take just occupancy grids as input and output surfaces as output such that the surfaces in some way represent the part of space that is occupied by the occupancy grid. Is this clear? Okay. As usual, there's no free lunch, and it's never this easy. That's kind of like one of the messages of this class. It's never that easy. But here is kind of one way you could actually calculate this occupancy. So what we're going to do to calculate occupancy is formulate the problem in terms of probabilities. And in particular, every cell, this is going to be basically a 3D, in 3D it's going to be a 3D floating point array. In 2D it would be a 2D floating point array where every number in the array goes between 0 and 1. If the number is 1, that means the probability that the surface goes through that grid cell, given the data that you have from the meshes, is 1. So that means if the probability is 1, that means that you are dead sure that the surface goes through there, given what you have observed from the surface meshes that were input. And if that probability is 0, for example, like it would be over here, then you are dead sure that the surface does not go through there. Now, how do we evaluate this probability? Well, one thing that you need to do is consider how you generated your data in the first place. And in particular, you don't want to assume that the data that you have in each one of your individual component meshes is perfect. And in fact, when I observe, or when I measure the positions of 3D points from my surfaces that I get out of my scanner, I say that the position of this point is right here, when really I'm not 100% sure. It could be back here a little bit, it could be up there a little bit, and there is some uncertainty. So to try to formalize this uncertainty, what you do is think about a sensor error model, which is to say, if my 3D surface sensor tells me that a point is 4 meters away, it might be 4, but there is a little bit of a probability that it's actually 3.9, and it could also be 4.1. And furthermore, I want to take into account the fact that, again, going back to this recurring theme, all we get when we measure a 3D surface one time is a discrete sampling of that surface. So in other words, if I measure the position, if I measure 3D points on the surface here and here, well, it doesn't mean that there's no surface here. It's not necessarily Swiss cheese. And in particular, I just want to account for the fact that I may not have observed the surface going through here simply because I discretely sampled that surface. So in fact, what's actually going to happen is that for every point on every 3D mesh, I'm going to essentially take the position of where it is as it was observed in my data set and smear it around. So I'm going to smear the probability that the point is there towards and away from the sensor to account for the fact that I'm not 100% sure that the point is actually where I said it was. That's what the sensor error model does. And I also want to smear it along the tangent plane of the surface to account for the fact that I am doing a discrete sampling of the surface. So in other words, this is saying, yes, there is a point at this location on the surface, but yeah, probably there are also points around it. So in other words, what we're doing is sort of painting the occupancy grid with probability. This is kind of maybe an unusual notion, but that's what we're going to do for every point in each one of our 3D point of view meshes. So if this is one of our 3D points here, and that's where the sensor is, like I said, we're not 100% sure, because our sensor has noise, whether the point is this far away or this far away or that far away. But it's more likely to be, the most likely position of it is here. That's why the sensor told us it was there in the first place. But there is some drop-off where there's a slight chance it's actually way, way up here. And there's a very slight chance it's way, way back there. So then I say, well, the probability of the point being here might be something like 0.5. And over here might be 0.2, 0.1, 0.01, and so on. And then again, like I said, if we've estimated that the surface tangent is in this direction, then I'm going to say, yes, well, I didn't actually observe a point at this point on the surface, but that's just because I'm doing this discrete sampling. So what I'm going to do is smear the probability that the surface goes through here along the tangent direction. So I have these two smearing of probability operations that I'm going to do. So for every point in each one of my meshes that I was given from my sensor, I'm going to take each point on it and smear it in the kind of occupied space in this way to try to account for these kinds of errors. So you add up those probabilities and basically average them over all points from all meshes, and you do this at every position in your grid. And if you do that, you end up with probabilities of the surface that look like so, where we have many, many meshes of the action figure dude here. And I'm, again, taking slices that go kind of parallel to the ground through it. So what you should see is, from calculating these probabilities, I then visualize them by saying probabilities that are close to 1 are white, and probabilities that are close to 0 are black. And the white stuff that's in the background is basically 0, but it's shown in white to try to tell you, to make it easier to visualize how far it takes for the probability to drop off from 1 to 0. So this stuff is not probability 1, it's actually 0. It's just far away from the surface. But what you should see is that, for example, in the stomach, where there's this bit of arm over here, there actually is a pretty good maximum here, where you can see that there's fairly high probability in most locations. And actually, the interesting thing is right here that since the arm is lower over here, it's actually really hard to image this part of the surface, because from a lot of points of view, it's occluded by the fact that the arm is down. So that's why the probability of this part of the surface is a little bit lower. So that gives you an example of real-life probabilities as you would get them out of this algorithm. So then what I have told you is that once you calculate these probabilities that every grid cell is occupied, you can then chuck the original meshes. So now no more meshes, all you have are these occupancies. So then there is a set of methods, although one has sort of taken over the world, for going from this kind of grid representation of your surface to one single unified surface. So then what you do is you basically threshold that map of probabilities so that every cell in the grid is either part of the surface or not. And then what you do is you use a method that has basically become the industry standard for this problem called marching cubes, which is to say from the center you add cells to a set of cells such that your set of cells goes all the way to the boundary of your original set of occupied cells. So you start from the middle and you kind of build cells onto it, almost like if you were playing with blocks and you were started with one block and you added blocks to it such that you kept making your grid of blocks larger and larger until they get out to the boundary of where your occupied cells were in the first place. So then, once you have a binary set, basically once you have a set of filled-in grid cells that are filled in all the way from the center of the object out to the boundary, you then have to do some reasoning about how you should convert the outer surface of those cells to a set of mesh faces and points. So, and the way to do that is to reason about for every grid cell that's on this boundary, whether my other neighbors are also boundary cells or not. So let's think about this a little bit. If my neighbors on this side, that side, that side, and that side are all members of the set of occupied grid cells, then I shouldn't have surface going through there at all because I'm not on the boundary in any reasonable sense. If this grid cell, the grid cells over here are filled in, but these three are not, then I can estimate that the surface goes through here like so, which makes sense. All of this stuff is kind of filled in, but over here it is not. Similarly, if these two guys are sort of in the interior and this is on the exterior, the surface has to go through it like so, and so on. So you basically reason about how the surface should cut through my occupancy grid given that I am on the boundary and my neighbors either are or are not. And you can enumerate all of the possible cases for all of your possible neighbors in 3D or 2D being part of the boundary or not. And that's exactly what marching cubes does. And here's an example of going from original component 3D meshes, each of which represents one point of view, to a final unified 3D model using marching cubes. So this example comes from the world of panoramic sensors of the type that you might have on your Mars lander or on your Humvee that is in the desert. So basically, you're standing right here and you get a 3D surface data set that covers the world around you. So the position at which you collect these things is shown in a color, and each of the points is colored by the type, the position that it was acquired from. So you can see there's basically two rooms here, and the 3D data points were collected from multiple positions in that room, in both rooms. And then they were aligned together using the techniques we talked about on Monday for doing rigid body alignment. And you end up with this stuff. And by the way, these points here shown in purple are the ceiling. So don't worry that those are some kind of terrible error. So if you align these two and then you do the occupancy grid approach to calculating the probability that basically the wall surface goes through every position in that grid, you'll end up with something like this that is color-coded the same way as before. And it should be clear that they've done a pretty good job of identifying in white the positions of the walls. So then if you run marching cubes on that, you will end up with a single unified 3D surface for all the walls around the room that look like so. And then you can rotate this thing and translate it and texture map it and do all the good stuff. But the point is that the thing on the lower left has one point in its data set for every position in the real world as opposed to multiple of them, which is what you have on the top left. Any questions about this? Okay. So So here is a failure mode of these volumetric methods. And this is one I had to find out myself the hard way when I was using these algorithms. So what I told you is that we take each point on each one of our 3D surfaces, and we assume that the most likely position of it is where the sensor told us it was, but also that there's some probability that it lies along a line closer to or farther away from the sensor along that line to the sensor. So if I do that, and I sense that there's points here and here, what I'm going to do is smear the probability of where that point is such that the most likely position of it is here, but there are also probabilities that it lies along this line in this direction and along this line in this direction. And let's say that the real, true underlying shape of the object is shown in brown. So then what's going to happen if I'm not careful is that instead of detecting a corner-shaped part of my object, I'm actually going to detect an X-shaped part of my object. So that if the probability of this point being over here is too large, and I actually threshold it and say, yes, by gum, the surface actually does go through there, then I'm going to screw up the shape of this thing. And this is a common problem in 3D modeling. It's that anywhere where you have high curvature, such as at a corner, which has technically infinitely high curvature, but you get the idea, then you have to sample that part of the surface a large number of times in order to get the shape right. Otherwise, you're going to confound things like this for things like that. And the reason this is called blowout is because when you look at your 3D models, it looks like your corners have had dynamite put behind them and they kind of explode outwards like this.
Yes.
Yeah. This class needs more dynamite. So just kind of to give you the high-level point of view of mesh-based and volumetric-based methods, they both have their pros and cons, which you will need to contemplate as the engineer who's building a system. Mesh-based systems are relatively cheap computationally. If you think about it, the only place where you really have to do heavy-duty computation is at the places where meshes intersect with each other, where they overlap with each other. So that if you have two meshes and 90% of the points in the two cover distinct parts of the surfaces, then you basically reduce the amount of things that you have to compute with from 100% to 10%. So you don't have to worry about and also, furthermore, it's intrinsically a surface problem, not a volume problem. So you can think of each of your meshes as being covering a two-dimensional manifold in a three-dimensional space. In this case, it's a two-dimensional problem rather than a three-dimensional volumetric problem that you're trying to solve. They're simple, but the problem is that there are no real guarantees about the properties of the surfaces that you get out. So a fair thing that you might ask, especially if you're a mathematician, is, so what is the topology of my surfaces going to be if I use this approach? Am I guaranteed to get something that has the topology of a sphere? In other words, there's no holes in it? Or could I get something that has the topology of a donut that has a hole in it? Or a double donut that has two holes in it, kind of a figure-8 shaped thing in some sense. No guarantees if you're using a mesh-based approach. And also, the other key problem is that this discrete sampling of surfaces is not really accounted for in the sense that it is in the volumetric approach. So if you have a very sparse sampling of the surface in some places, there's a chance that you could completely cut a hole in that part of the surface. There's no formal mechanism for dealing with that. And also, even though you may try to connect meshes with each other nicely, there's still good odds that you are going to end up with slivery or small triangles that form a seam that is visible. Volumetric approaches, on the other hand, especially if you use marching cubes, which gives you this guarantee, are guaranteed to generate a two-manifold without holes. It's genus 0, topologically simple. If you have something like a gnome that is like a statuette, you are guaranteed to get something that is a statuette with no holes in it. And another plus, as I have mentioned already, is that after you calculate these occupancies, the computation time doesn't depend on the number of meshes. Getting a surface takes the same amount of time after this step if you have 5 meshes, 100, or 1,000. So that's nice. And it also explicitly represents your uncertainty. So it really takes some knowledge about where the data came from and incorporates it into the algorithm in a way that the mesh-based approach doesn't. The key downside is that you are representing the entire world, period. So, and you have to have some number of grid cells that you discretize the world into. So how much you discretize is going to determine the fidelity of your final model. You cannot represent the smallest 1 centimeter by 1 centimeter by 1 centimeter cube of the world in terms of a million, zillion, jillion voxels because they won't fit into memory. But you really need to do that in order to get a perfectly high fidelity representation of the surface. So it's expensive, and the resolution depends on how much space you can give it. So putting aligned meshes together into a unified model is important in ways that I've described. And the two approaches are mesh-based and volumetric-based. Any last-minute questions? OK, thank you. See you Monday.